let's continue for the encoder. So this is the last time we see is a 5 to 3 encoder. So last time we went through the truth table. This is input, this output. So when you activate one input, you will receive 3-bit output for this 5 to 3 encoder. So out of these 5 inputs here, we only can activate one. You can see that there's only 1 0 because this is active low, so we have only 1 0 for each row. Each row can have only 1 0. So this time we're going to look at what happened if the user input 2 0 on one row here. If input 2 0, what will happen? Okay, let's look at the first scenario. Let's redraw this again. Let me copy this, the whole thing again here. So this is the case study here. We try to solve some problem here today. So let's use a different color. So what if, okay, what if the user input here 2 0? Okay, let me erase first. Let's erase this one first. So if this is 0, so if the user input 2 0 here, what will be the output? This 0 will output 1 and 0. So 1 and 0. Okay, no problem, because this is OR gate. Remember, OR gate only one activate here will change the output. Only for this case, only 0 will change the output here. Okay, so if 2 0 activated, if 2 of this input activated, here is still 1. 1 0 activated, you receive 1. 3 0 activated, you still receive 1. This is OR gate, right? You remember OR gate? Do you remember OR gate? Let me show you one scenario here. Let me do some review for the OR gate. So let's assume we have 3 input normal OR gate here. 3 input. Let me create two scenarios here to explain my point. So if you have only 1, you output you'll get 1. Okay, if you get 3 here, output is still 1. You won't get 3. Okay, it's still 1. This is a logic. So this is the fundamental. So let's come back here. So this activated output A2, you will get 1 0 here. So this 1 you will get definitely, because active high, right? This active high, so you'll get only 1. So the output is still this one. This is correct. Okay, it's still this output. But the problem is, if the user they want 2, you output 3. No, let's assume the user want if the user press these 2, we have to decide whether which outputs which one should we use to output the data. So in the normal case, we will choose the highest one. The highest one, that means if we receive these 2 input, we will output 3. So this is correct. This is correct based on we output only the highest one. Okay, then how about this one? How about the second row? How about the second row here? So if we receive 2 input here, this input will get this output here. So this one become 1. Okay, so this one will become 1 here. So this one become 1. This will become 1 because of this first row. When 0 here, you got 1, you get 1. When 0 here, you get 1. When this one, you get 1, 0. So we get is 3. So if the user press these two together, 1 and 2, we decide to select the highest one, A2. This is not 2. This is not binary code for 2. So this is wrong. So this is based on the highest based on highest input. Okay, let's look at another case one. Let's say this one we change to 0 here. This one change to 0. I just simply change any one here. I randomly choose these two to be activated at the same time, or we can choose 3 activated at the same time. Now let's do this one. So the two will output 1 0. So we'll get 1 0 here. Okay, so this change to 1. This change to 1. Two will output 1 0. 2 will output 1 0. Now the user press 4 and 2 together. If we choose the highest one, which is 4, we should get 1 0 0, but we get 6. So this is incorrect. This is not what we want. So we tested 3 rows here, and then we can find that if the user press only one input here, if the user only activate one of the inputs, the code we get is correct, correspond to the input code. 00001 correspond to 1. 010 correspond to 2. 011 corresponds to 3. So if the user activate only one, we'll get the correct codes. Okay, this encoder, remember, we need to output the codes, the correct codes. But if the user input 2, activate 2, sometimes by mistake, sometimes it happens, okay, sometimes due to the circuit, due to the timing issue, we have received 2 activated. When 2 inputs activated, the code we get, if we choose to based on the highest one, let's example 4 and 2 activate together, we choose 4. This is not the code for 4. This is a 6. 110 is a 6. It's not 110 does not correspond to 4. So apparently this truth table cannot be used if the user activated 2 inputs or more, or 3 inputs or 4 input. Assume all this input is all 0. The code produced cannot be used. It's too random, cannot be used. That's why this brings us to the next topic. So the next topic we're going to talk about is the priority encoder. So today this is number 1. Better start number 6. Okay, let's continue from the last one. So today it brings us to the new topic here. Is extension of the encoder. This one is the we call the more practical kind of encoder, just like the ADC. Remember the ADC topic? The digital staircase digital is very simple, but it's not practical. The second type is called the successive approximation ADC. That one is quite faster than the staircase, and the successive approximation is the one commonly used in the market. And the third type, flash ADC, is not practical, only for theory use only. So this brings us to the next topic called the priority, which we call it. Let's do one example. 4 to 2. 4 to 2. This word we insert a new word called priority encoder. It's no longer a normal encoder. This encoder is called priority encoder. That means we will choose the highest one. Okay, let's look at the truth table. let's design the truth table. We have I3 input 3 4 to 2, so we have 4 input here. Four inputs. Okay, and 2 binary output here. Let's use the D. Let's use D for output. MSB D1 and LSB. MSD and LSD. Okay, so what do we mean highest priority? So let me show you. So this is active high. Both are active high, the most simple one. So let me remind you again. This is active high. Here also active high. So we don't need to worry about active low issue here. Both are the same type here. So when the when this I3 is activated, no matter whether you activate this one or not, so we use a don't care. Is it 1 or 0 here is not important anymore. If this one is activated, the output must be 1 1, which correspond to 3. So you get the idea. You get the idea of this priority encoder. It means when the number 3 is activated, 2 1 0 don't care anymore whether you activate or you don't activate. We don't care. Okay, we just look at the highest one. This one is called the priority encoder. That number 3 has the highest priority. So this mean that I3 has the highest priority. Okay, the second row, the I2 has the highest priority. This is the common truth table here for the priority encoder. So the I2 has, when I2 is activated, don't care whether you activate I1 or not. I don't care whether you activate I0 or not. The output should be correspond to 2. But can we say this don't care? Cannot. If we say this don't care, that means is what? That means that it's already confused. Because 3 is higher than 2, what do you mean don't care? We cannot put a don't care here. We have to put a 0. You know why do we need to put a 0? Because remember, the definition for encoder is only 1 can be activated at any time. Okay, only 1. But here is the case slightly different, because we look at highest one. If the I3 is activated, I don't care about this 3. If the I2 is the highest one, I don't care about 1 and 2. But you must not activate I3. If you activate I3, that means if this is 1 again, let's say this is 1, that means you activate I3. If you put 1 here, that means you refer to I3. If you do a don't care also, you refer to I3. That means we follow the first line. That means I3 activated. You get what I mean? 0 means I3 deactivated. I3 cannot be activated. This we put a 0. If we put a don't care, that means we choose I3. If we put a 1, that means we choose I3. Which one? We just do the first row enough. We don't need the second row. So for the third row, if we receive a 1 here, I don't care whether you input 0. This output code correspond to the 1, which is 0 1. Okay, so this must be 0 and 0. You cannot activate these two. Then I will follow. You input 1 1 here or 1 0 here, you always get 0 1. Okay. This meaning of the priority. So the last one is 0. If you enter 0 here, you will get 0 0. but you must not activate the one highest than 0. So this is priority encoder. So now the problem is how to design a logic table, how to design the logic circuit using the this truth table, which is looks very complicated because we have all these now don't care things we learn in the digital one. Okay, let's go right into this design. So to design this, we need to use the Carnot map. Okay, we need to use the Carnot map for D1. For we have two output here. For output, we need to do it separately. For output D1 got the one logic function, D0 also got another logic Boolean equation. So we focus on D1 first. So let's use the Carnot map. So this is 4 input here. We got 16 possibility here. We got 16 possibility for the 4 inputs here. Remember for the Carnot map. So let me quickly finish this 16 square. I think later we can copy to the next one. So this is one. Okay, this is center one. So this I3, you still remember from the digital one, I2, I1, I0, I1, I0. So you remember this, the sequence 0, 0, 0, 1 is 1, 1 first, right? Then 1, 0. You must not forget about this. This is really a very common tools we use in simplify the Boolean equation. Okay, now I copy this to the other side so that we can reuse again later. Let's copy this before we fill in anything. Let's copy to the other side here for D0. Okay, now the problem is how do you fill in this Carnot map here from the data we have here? How do you fill in for D0? Okay, you see now we focus on only the one. Let me use the black color. Okay, let's use black color will do. So let's focus on this one here. So this one here we have I3, I2, I1, I0. Don't care means what? It can be 1 or 0. So let's assume all 1. 1, 1, 1, 1. D1 here, D1 here, D1 here. 1, 1, 1. 1, 1, 1, 1. Okay, 1, 1, 1. Where's 1, 1, 1, 1? Here. Do you understand? This oh sorry, 1, 1, 1, 1 here. Yeah, 1, 1, 1, 1. But this can be 1, 0, 1, 1. 1, 0, 0, 0. Anything start with the 1, we need to activate. Anything start with the 1 here. Anything start with the 1, because you don't care. Anything I3 is 1. Can you follow? We look at this one here. We look at this one here. Anything I3 is 1, don't care here, we'll get 1. So anything I3 is 1 here, I3 is 1 here, all will get 1. So what is the next one? Anything I2 here, but I3 must be 0. It means this I3 0, I2 and whatever here must be activated. One more time, this row is slightly different. Anything start with I3 0, I2 1, don't care here, we'll get 1. So look for I30, I21, I30, I21. Don't care about the I1 and I0. Okay, all get 1. So this is the Carnot map we have. Now let's circle it. You know, to circle this, we need to choose 4 in a group or possible 8 in a group. But currently we can see there's 8 in a group. One, this one is 8. We just group this 8 into 1. Okay, so this is the first one, and then we group the next one 8 into 1. Another group here. We got 16. We want to group 16, but we couldn't find 16 here. The maximum we find is 2. So this one is from the Carnot map. From the Carnot, this 8 is above all cancel each other. We look down here. 0 and 1 cancel. 1 negative, 1 positive. Sorry. Because of this one. Okay. If you have this one inverted or this one, you always get 1. If a 0 inverted, you'll get 1. If a 1, you'll get 1. So if a 1 and 0 together, you'll get 1. So what we have is I2 here. We have I2 here. I2. Because of this. This corresponds to I2. So for the second group here, all I1, I0 cancel. So what we have is here. I2 cancel, we left with I3. So here's I3. Okay. So let's do the other group. Let's do this group now. I hope you can follow. This is the all digital one. We cannot spend too much time on digital one because we do not have time for the new topics here. So I need to proceed. If you don't know about this Carnot map, you need to review it yourself. You need to review yourself. So for output, D0 now. Now we look at this D0. I hope you can feel it now. For anything start with I3, I don't care about the rest. I get 1. One more time. Anything start with I3. When I3 is 1, I don't care about this 3. D0 will output 1. Anything start with I3 is this 2. So 1, 1, 1, 1. 2 rows. So the next one is here. Anything start with 0, 0, 1. 0, 0, then I1 is 1. What is it? 0, 0, and I1 is 1. Here and here. Wait. 0, 0, 0, 0. Wait. Here. 0, 0, 1. Okay, I1 is 1. Where is I1? I1 is here. This I1. This I1. This not this. This I0. Very confusing, right? I3 0, I2 0. Hey, wait a minute. Here. Anything start with I3, don't care about this. Is this 2 row. Okay. Then we look at this. The next one. 0, 0 is here. This row. This 4. But I3 is 1. I don't care about I0. I3 is 1. Oh, sorry. One more time. 0, 0. I3, I2, 0 is this first row here. First row. But I1 is 1. I1 is this digit. I1 is 1. This I1 is 0. So you need only these 2. Okay, now let's circle it. For the bottom one is simple. Bottom one just like the one on the right here. The same thing. And now we can group 4. We don't want to group 2. We will try to group as many as possible. We group 4 here. Okay. So this one would be similar to this I3. This one would be the top one, 1 and 0 cancel, we left with I1. We look at the to the left hand side here, I3 cancel, we left with I2 bar. We left with I2 bar here. So we have, now let's write the real Boolean equation. Write the Boolean equation. D1 is equal to, let's write it down properly, I2 or I3. Very simple, right? D0 is, let's write the I1 first, okay? I1, I2 bar plus I3. I think now you know how to draw the Boolean equation now, right? This is the most easiest part here. Okay, let's start with the 4 input here. Let's start with 4 input. I3, I2 to I0. So what we need is OR gate, and gate, but OR gate is more important. The output is OR gate. Okay, let's, because remember the first day I told you that encoder using OR gate. So this is the active high. This is so easy. So this would be our I1 or D1, sorry, D1. Don't confuse with D1. So another OR gate here. Another OR gate. Okay, draw properly the OR gate here. So this is D0. So for the D1 is easy. I2 and I3. What do you mean I2 and I3? I2, I3 means you just link I3 here. Just link I3. Because active high or active high, right? It's easy. There's nothing difficult here. I3 and I2. So draw I2 down here. Extend I2 line here. Extend I2 line. Connected. Link to this. So this one is equal to I3 or I2. Or I2. Similar to the one we get. So this one is slightly complicated. We need to do this one first. I want I2 first. I want I2 first, and I2 must be bar. So the to do this, I prefer to use AND gate first. I use AND gate. I use here I2. We need I2 bar. Remember I2 bar. So we need the inverter here. Even though sometimes I try to do it very fast, but I still need to make sure it's clear. We cannot sacrifice the all this clarity for the time. Do it fast, but we'll do it properly. So this I2 bar, as you know, this I2 bar, right? Let's write down here, I2 bar, so that people know. So I2 bar and I1. There's no I0. I0 is not being used, so we can ignore the I0 here. So the I1 here. I can draw it because I0 is not being used. There's no I0 here. Otherwise, I won't get over to anything near the I0. So that's it. Also, let's finish this up. I1, I2 bar, or I3. So this is our encoder. Sorry, one. This is our encoder. This is the 4 to 2. So if you, too bad I cannot select the dotted line here, but I want to show you if you draw the dotted line, this, okay, inside this dotted line box here, inside this dotted line is our 4 to 2 priority encoder. I3 in, I2 input, I1 input, I0 input, and then we got two output here, D1 and D0. So this is our, how to call this, everything must have a name. This is called 4 to dash 2, remember the important word, priority encoder. It's not 4 to 2 encoder. 4 to 2 encoder is too simple. This 4 to 2 priority encoder based on this two table. So I hope you understand this topic. This is a really important topic. So I'm quite sure in your final exam I will use this as a question. But of course I will not use 4 to 2 right? I will most likely use the 5 to 2 or 6 to 3 or this priority encoder. But you have to make sure you know how to design this, okay? You have to practice the whole thing on your own. Get a piece of white paper, blank paper here, and start with a blank paper. First you need to design the correct truth table for this priority encoder. Then you do the K-map, and then lastly you draw the logic circuit. Then this is a block diagram, the simplified block diagram to represent the whole thing here. Okay, this is a 4 to 2 priority encoder.